Good morning, and I didn't say I don't need an introduction, I said I don't want an introduction. There's a very big semantic difference. We should have a slide deck that's actually bothering to move, if I can get my clicker to work. Come on. Come on. Okay, I'm using my fingers then. I hate talking in I hate talking in the morning. It does never go well. Okay, I unfortunately am the other person in the room who started doing Go the day it came out. I've never done anything useful in the community. I bum around, it's my hobby. The last time I was in Berlin was 2008 to talk about Ruby at a Rails conference. And when I say Ruby, I actually mean networking and cryptography. And I gave the first ever talk outside of Google, as far as I can tell, on Go. That was in November 2009, on my mad dream to port TinyRB, a small Ruby runtime, to Go. I still don't know enough Go to do it. I'm sorry. People ask me the horrible question, what do you do for a living? I don't know the answer to that. I do know how to say but not the answer. So, I do evil things that sometimes result in patents. I'm sorry. In, I think, 17 years' time, everybody can use this system at the bottom. It gives you a free back channel in a web connection so you can turn somebody else's browser off remotely. That's the kind of stuff I work on. We are going to explore functional programming this morning, and we are going to learn how to write Ruby and Go. Sorry, again, for that. Everything that I'm going to show you works. None of it's a good idea. Please don't do it in production. Don't do it on main. Don't send me tech support requests. I don't answer them. So, this is functional programming in, I think, 11 slides. We're going quick because I've now only got 28 minutes and 45 seconds left. So, we're programmers. We use the word function to mean a random recipe that we got out of a cookbook that we're going to inflict on some poor, undeserving machine who really wants our love and forgiveness. Mathematicians use the word function to mean something a little more precise. In maths, a function is a mapping, such that if I put 6 different labeled balls in a bag, and then I say, I want the third one out, the third one that comes out will always be the same, it won't be jumbled, and it will always say the same answer. That's a function. You don't use functions most of the time, deal with it. This introduces a concept called a pure function. All the functional programming heads, and I've been to some of their conferences, and they're really insufferable. But anyway, they'll go on about how you can't write software without them because you have side effects. And then they say things like monads, and the next thing I know, I don't have any idea what the code on the screen looks like because it's line noise. But in this particular case, I'm going to give you a pure function, and as we have them, there's some generics. This means that I can express a single add function that will happily deal with a pair of ints or a pair of float 32s, and I never again have to write a sodding type switch and figure that out at runtime and suddenly go at the speed of a basic interpreter. So, we'll skip past that. Global variables are Satan's own creation, and he play a very important part in reality. So, sadly, I have color-coded. If you see something in this disgusting shade of orange, it means it's probably not a safe thing to do. In this particular case, accumulate looks like a lovely, sensible function that adds things up. The trouble is, I can also add to my sum variable elsewhere. So I cannot guarantee that what I accumulate results in the answer I expect. So don't do it. This is more of the same. Oh yes, it's an impure, this is an actual function-ish. The difference from the other one, no return value, definitely not a function, ever. A return value that could be wrong, kind of a function. Think of it as kind of like a spectrum of function behaviors. This is a non-binary function. This is a, well, wrong way. This is a FU function. And this, of course, is on a method. So unless I get close with this thing from the right kind of object, I don't know if it's a function or not. So this is the trick I want everybody to learn and take away. This is really the most important thing in the whole talk. I can actually have local persistent state that behaves like a global variable for just one function. And if I run make accumulator, each time I run it, I will get a different function that behaves the same way, but has its own global variable for storing stuff. Now you can have as much sodding mutable state as you want, and functional programmers can off. So, right. We can also do that on objects by sticking it in methods, duh. And we can go a little bit further, because then we can have other methods that do things. So down here, hold on a sec. I normally look at this, well, I would normally be looking at this from back there, because I really don't like being in front of audiences. So, in this little one down here, you'll notice I've overshot. Let's go back. Add, make accumulator. Down here, I might sometimes want to cast the value stored in my accumulator, which, as you will notice, is a lot of different kinds of numeric type. And as we tend to have int plastered all the way through the standard library as a way of doing it, I can do that on an object. And now I give you back a function, and you can actually, have it play in the standard library using structural typing. So pretty much everything about typing has just been covered. This one down here is just in case you find yourself being given something you don't know what to do with, or something that implements accumulator but isn't actually a numeric type. You can put a third line in there if you want to take an any and work it out for yourself. You can put a fourth line if you want to accept a reflect value, and then you can take anything from anywhere and turn it into anything. There's a reason I don't get asked to talk in the States about this stuff. And just for fun, we can introduce our own intish interface. And then, yes, it's not very interesting, but anything that can return an int through intish, which is tons of stuff in the standard library, now works with our accumulator. Bye. That was everything I wanted to teach about functional programming. All that stuff about immutable state, forget it. The real world doesn't work that way. Now we're going to do recursion, which is great. I've got 22 minutes and 58 seconds. This is a recursive function call. Does anybody know what happens when you make this recursive function call? You exhaust the stack. So I don't know if this works across. I don't actually know how Go does any of the low-level implementation. I have been avoiding knowing that for 16 years. Because I do not want anything to get in the way of my doing what I want to do. If I knew implementation, I'd make different choices. You should make different choices. I'm not going to, right? On my MacBook Pro, which is still Intel, this does about 16,700,000 recursions, and then it goes bang! Your memory might vary. I want to do that. You can't do that because I've exhausted the stack. I can't create a stack frame to run the damn deferred function. So, recursion, it can be a problem. We're going to look at one of the most boring and tedious problems in IT, the one that we're all being asked all the time to solve in our computer systems, obviously. Computing factorials. I'm now going to mime from over there. So just for the avoidance of doubt, if you use 64-bit integers to calculate factorials, you're not getting very far. This actually will do 20, but not 21. After 21, you'll get some interesting overflow errors, And then around about 63, it settles down to 0. Things you learn. It's a boring old problem, it lives in the maths world, but it's got this great advantage that it is naturally recursive. I mean, that's the definition of factorials. So, we have 3 values that a factorial can return. If we give it a 1, we will get back 1. If we give it a 0, we will get back 1, for reasons I once tried to find out by deep diving every article on the damn subject I could find online. And no one in maths can give me an answer, apparently. But 0 gives you back 1. -1 does not give you anything. It is an undefined error and should panic all over the place, because it's an actual, genuine, unrecoverable error from the point of view of factorials. There's another category of math that allows you to do it with complex numbers, but only positive ones on both axes. So 3/4 of, well, I say 3/4, I mean it's an infinite range, who knows? But 3/4 of complex numbers do not have a factorial. I think that's kind of, you know, unkind, unfair. Anyway, we've got this stupid sodding problem, and we're going to turn it into code in case we're ever trapped in a code review, maybe in an escalator to hell or something. Expressing factorial is really simple if you take out all your error cases before you actually get to the factorial function. So in this little example, I'm going to range over parameters on the command line, because why wouldn't you? And then I'm going to make sure that what I get can be converted into an integer of some variety. And then I'm going to make sure that it's not below 0. And if it's either of those two things, I'm going to say no defined. And otherwise, I'm just going to print out whatever the factorial comes back. Lovely safe code, unless I run out of stack or want to get an incorrect answer above 20. The actual factorial function itself, when I've taken all the error handling out, just becomes this little thing. If 0, return 1. That's weird. And otherwise, go off and do factorial. Right. I promise this problem is actually relevant to something that actually is much deeper and more interesting. So over here, I would prefer to use a panic on this, because my program shouldn't even try and do any work. So I'm accidentally going to teach you how to do exception handling in Go. Don't do it in a production code place. Please don't set anybody on me. Sorry. Oh, I do, by the way. But you shouldn't. So in this case, I've changed my logic around a bit. Now you'll notice I don't actually calculate it if x is less than 0 as a test. I do x is greater than -1. A, because as Dave said yesterday morning, these are easier to read. And B, I was an assembly language programmer for a decade, and that's fast. It's such a stupid amount not mattering on a machine that can read a register in 0.24 of a nanosecond. It doesn't matter. This machine can read a register in 0.24 of a nanosecond, and this is 8 years old, right? That it doesn't really matter, but I'm afraid bad habits get ingrained. Here, I'd like to catch those panics and print my message out, and the rest of it I just like to run through. This works, but this works for an odd reason. Because you may notice that I have got that defer function inside a func. Why have I got an anonymous func there? Because defer runs when a function exits. If I didn't have this anonymous func, that panic would cause one defer, and then we're straight out of main. I couldn't skip past values. Now, I don't ever do live coding. This is the closest I'm going to get to anything live. And this probably isn't going to work, because I'm now going to have to, and they've done stuff with the video, and everything's going to go hideously wrong. Plus I can't see close up in my glasses. But this is roughly what we're looking to get. And I'm going to have to, hold on. I am not at the resolution I thought I was. So, make this really big. This is actually where we're going to end up at the end of this. But if you notice, amid some of this garbage that's coming out, this debugging, we get no factorial defined for dog. We get no factorial defined for -1, and then we get some factorials defined for other things. That's just to prove this does kind of, whoa, no, that's the wrong slide deck. We won't get, we'll see that slide again, that's the whole reason why it's there, because I cut and paste it. I'm not a very organized speaker. Right, so this little trick here, this allows us to actually do panic, recover, as a way of doing local exception handling. You can wrap this up in code. We'll get there in a little while. Oh, lucky me, I thought of that earlier. Now I've got a slightly different layout, and 20 years ago, that would have made less thump. Anyway, I used to stomp around the stage in 5-inch heels 20 years ago. My back can't take that anymore. So I've introduced this function down here, catch. Now, this is an example of a kind of function used all the time in functional programming. It's a higher order function. It's a function that takes a function and either returns a value based on what it did, or gets it to do some stuff, or gives you back a function you can use later. Any one of those three patterns. In this case, I don't want to have to pepper defer all the way through my code. So I return a function that will do my defer on the function I give catch. And then when I call that function later, it will actually, this f will get activated, and the actual payload will happen. Now, this is also an example of something called currying. Currying is named after a mathematician, Haskell Curry, who discovered a lot of the cool tricks in the functional programming world, but looks a bit crufty. I think we see a photo of him later. This means I can set up this catch at one point in my program, and I can use it as many times as I like. And each time I use it, I can use it with a separate payload, but I always use the same defer. So don't put state in the defer. Very important. Don't put state in places that you might run more than once and you don't want state. There you are. That's immutability's real purpose. Now, oops, if we skip on from there, you'll also notice I'm effectively designing a DSL, a domain-specific language. And if you run over into the functional programming world, they don't even bother talking about them that way. But if you've ever been a Rubyist, you'll know that other people go, but I can't read that code, that's not Ruby. And you go, well, of course it's not, it's a DSL, silly. Yes, this is the language we actually wanted to write in, we just used Ruby to write it. And then they go, oh, can you show me the interpreter? It's like, don't be silly, Ruby is the interpreter, dear. So, up here, we'll always be able to do that recover, and that's just the thing that matters. This can be kind of hard to read and think about when these two things are separated too far, though. Because now I've got a panic, and where the hell does the panic go? This works fine in functional programming because functional programming is all about recursion, so it's always in scope where you're going back to. If you do this in conventional Go code, you will drive yourself insane trying to debug it. That's why you shouldn't do it. See? Yeah, I give advice. Now, I don't actually like all of this boilerplate having to turn up there because it makes it difficult for me to see what the intent of what I'm doing. This is refactoring, by the way. There were books on this subject. They're very tedious. They never get to the point. So, which is, we're programmers, we should be lazy, write the least amount that you need to. You can make your functions as small as you like, as long as you can actually understand them. So in this case, we've now got a DSL that has the concept of catch for error, that has the idea of no defined values where it will go off and do some work. And I decided to make the no defined values, which creates a function, I decided to make it take a string. So that, Oh, 11 minutes, we're doing well. So it can quite happily deal with different kinds of no-defined values. So if I wanted to use this with a Fibonacci sequence, I could replace my parameter factorial with Fibonacci. And my error message will say, no Fibonacci defined, no something defined for Fibonacci. See? This is generic code, this is reusable code, this is lovely, this is why people write all those long papers on functional programming. And then they write it in Haskell with angle points and letters and line noise. But that's mathematicians. Right, so we can reduce that down now by also saying, well, that print factorial thing, we keep putting that in on in line. Well, that's really a bit of functionality we'll probably want separated out. And suddenly we've got a main program that's, well, skip undefined things by catching no defined value. Oh, and by the way, go off and do a whole pile of print factorials while we go through this loop of values we take off the command line. Yeah, this stuff's easy, honestly. Don't believe people who say it's hard. Oh, but you do have to know what this would look like if you wrote it the way a mathematician or functional programmer would. So, there's a lot of anonymous functions in here. No, I can't read that. I wrote it, I can't read it. But these little anonymous functions here, they're very important, because this is a basis of, this is basically lambda calculus, and we'll get to that in a minute. 9 minutes, 20 seconds. Right, so, thing is, the whole reason I got sucked into thinking about this stuff in the first place, because you should put a personal anecdote in, you see, as part of it all. And it's 2009, and I got off a plane, and the nice people in the States released Go, and I just spent 6 months explaining to people how they should do kernel scripting in Ruby on Unix boxes. And I've been showing off all the Ruby tricks, and this is kind of a plug, because I'm giving a talk on how to do this in Go at GopherCon UK and a workshop at GoLab. Please come and see me, they can all do with the money. And I just wanted to implement a simple forth to get me started. And forth has a stack. Well, that's all right, that's a stack type that can intermingle floating point and integer values. Oh, shit. Oh, I should probably be region-specific. Oh, scheisse. So I started a whole pile of repos that nobody uses, please don't, that are attempts to solve the collection problem before we had generics. Just use generics. And each is an example of one of the most basic patterns, a functional iterator. So in this case, oh, by the way, it's awful because of stack exhaustion, and we don't have tail calls, where you can keep the same stack frame each time you come back from the previous function call. So you don't have to keep allocating on the stack, and it doesn't go bang. If main had tail calls, I would show you a different talk about what you do when you can't deal with the halting problem. I used to know what it was in German. All the papers are written in German, in English papers, but the German name, Einsteiger something problem. Anyway, it means we don't know if it will stop. We do. There's heat death of the universe. Plus also there's an electric bill. So in this particular case, we're just going to recurse along all the values, which now means up here, we can write this little function each. So now, I'd quite like to catch any no defined values for a factorial. And it would be quite nice if I could do that on each instance through a set of parameters. And that's actually really readable code. And some of the other code to go with it, though, wasn't. I'll go back. Well, too far back. Right. Now, you remember that little trick I showed you earlier about creating local global variables for a function? So, I can take that whole idea of doing the factorial calculation, and I can stick a hash map in the middle of my generator for the factorial function. Now, this has the advantage, I will only have to calculate each value once. But if you decide to ask for 20 first, I'm going to calculate all 20 values, and then you'd better run it more than 20 times. It'll amortize over time. If you're doing it as a single shot, it's not worth it. But if you're doing it 100 times, it's worth it. right? And then as a result, I get to have this memory. I don't really want to talk about that much because, I mean, it's fairly... Oh, there's a little trick. You'll notice I check to see if there's a 0 value in the map. That's because the 0 value means I haven't yet written into the map, because 0 is never the answer of factorial. So it's an optimization. You come for optimization tricks too. So, now we get on to the actual meat, and we've got 5 minutes and 38 seconds to describe something that once you know it, it's so damn obvious you can't see it, or can't not see it. But until that, you keep scratching your head and going, but why does this matter? The Y combinator. So, this recurses because main is a named function, so I can use the name. How do I recurse that? It hasn't got a name. I can't refer to it inside itself. But all of functional programming is based on anonymous functions, and only works if you recurse. Well, we get our lambda calculus from this nice man, Alonzo Church. And his lambda calculus is mathematically identical to Turing's model of computing, which is all about moving things and measuring or writing them and moving back again, right? So we know that lambda calculus must be able to do recursion because my bloody computer, which tries to be a Turing machine, sort of, can do it. So that's a good start. Well, it turns out in maths, there's this funny little idea called a fixed point. If I have a function and the value it returns is the same as the parameter I give it, this is called a fixed point. And to mathematicians who originally, this was kind of like, well, that's an interesting trivial point, isn't it? But why am I interested in a particular value? Well, it turns out in lambda calculus, I can use fixed points as if they were names. And then I can have these horrible expressions like this, please forgive that. Or visually, there's a language called Vex. This is what I'm about to talk about looks like, and it's a complicated machine on either side for getting an X. Oh, I've got to press this twice. Sorry, I don't normally do animations. Right. Well, it turns out that Mr. Curry, who we get currying from, also found this funny little thing called a Y combinator that does that horrible bit of math, but which we can express much more clearly. So we're going to build that machine in 3 minutes and 19 seconds. If you don't believe that's possible, I've done the whole crypto and networking stack in 4:53. So up here, we're going to have a factorial function, and it's going to have an anonymous function that does a calculation, and it's going to use this thing y to create a function that actually recurses. So factorial will recurse. I promise that is true. The code that you saw me run earlier, we'll get to the end, and it is exactly the same thing going on, okay? And we've got all of our boilerplate, which I'm not really very interested in, except you'll notice we start to get functions turning up as parameters, and then, oh shit. What the hell's that? Well, if you remember that slide a few back with all the lambdas on, that's the easiest way to express that in Go. This is completely untyped, which is in the spirit of the lambda calculus. Except I have to force things to be specific types when they execute, which you'll notice are functions of any to any. Yeah. I'm back where I was in 2009 with my first ever talk, which was all blank interfaces. So I'm not going to walk through that. What's important is that parameter up there, that parameter there, G, is that function, that's our payload. And in fact, I probably should have called it payload, but I tend to use one-letter variables in functions. And I want to return that payload when somebody calls my recursor. So I'll skip past this. Oh, God. We're into the world of ellipsis now. You know it's bad. Double ellipsis. Right. So we're going to start introducing some human-readable language. And along the way, we're accidentally going to end up with fully typed lambda calculus, which I didn't know I could do, and I've got 1 minute 19, so we're speeding up. Right. The point about this is I can give function a name. I can also introduce an idea of a recursor that does the recursion aspect, and that gives me back a function. So some of my type signatures will start to collapse. And you'll notice down here, recursor, because it gives us back a function, is directly executable, no costs. So we're starting to have readable code. I can also have the idea of a subtype of function called a transformer. Now, a transformer takes a function and gives you back another function. So it's basically the same underlying concept as just a function. But now I've reduced the scope of the type so I can do some clever crap. Boom. And in here, I'm now using two recursors. I've broken out a whole pile of boilerplate into just these two recursors. If you remember that diagram from Vex, you've got the two balls with an X in them. That's why. It takes one ball to create the next ball. This is why I'm not an academic. So we come back over here. Some of our casts have changed. If it's in blue, it's to do with types. I thought that was probably easier. If it's in some shade of purpley red, that purple or through pink, that means it's level of scope, so your eye can follow it. I've still got some casts in there I don't like. And I really would like to cut out all of this absolute and just actually have what y is expressed as in its most natural form mathematically. A function that calls another function that's been called by y. So y calls my recursor, and then my recursor calls the thing that y gave me back. This is how I put names on unnameable things, right? And I want to express that, and I can express that directly, sort of. Because my g here is doing all the payload of y, and I can give g, therefore, another g, which happens to have been created by the full body of y on itself, and it will work. It's like, whoever your favorite stage magician is, they're on stage, and you're thinking, but they shouldn't have hands now. I saw the blade come down. And that's exactly what this is, that kind of trick. I've also introduced the idea that a recursor can have an apply, an application. You'll find apply and bind are the two things you find in the functional world. Apply is make a function run with a particular bit of state. And then bind is put this state on this particular label and keep it there forever. And so down here, we can use apply. And up here, all our type signatures that we had for doing the cast have basically disappeared because everything is now quite tightly typed. Right, I'm not going to talk about that one because the sole purpose of it is we've now generalized type. I didn't anticipate having to pull the top up because of jumping, because I was going to be down there. It was going to be much cooler with the laser pointer. So, right. So in this case, I've got two generic types that I take for this, not one. Because I might want to take a parameter into my function I'm going to recurse with that's of a different type than the value I want to give back. So this is a fully generalized version, right? No, even I'm struggling to remember why that one mattered. Now, wouldn't it be nice if we added the local state back in as well, so we don't have to do any calculation of things we've already calculated with a Y combinator? Boom. So that will do exactly what you've seen done, and is exactly like the example earlier down, which is much simpler to read. And we'll skip past that. He does some fluff and blah, 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 don't care. 31, I can now take the concept of Y, and now I can separate that out as a factory for particular versions of a Y to implement. And in my code here, I can have two different Ys that I've created. And you'll notice up here, I take a map as a parameter. These two Ys, even though they do the same thing, factorial, they have different backing stores. I don't know why you might want that. I could only speculate. But it's kind of cool. Now, is kind of cool. This is the only talk in the world that will not only show your Y Combinator, get it into fully typed in your own language, and give you local storage, but will also mean that you can have multiple backing stores. I keep raising the bar on this because people keep doing their own versions in Go, and I wish they'd stop. So there only needs to be one. It's math. Right, so there is other stuff that you can find out about this particular topic. Firstly, the same conference series I gave my first Go talk at was Ruby Manu in London. This guy, Tom Stewart's an academic, but he's an academic that you can actually understand what he's saying. He's written a book, I think, called Explaining Computation, which is on O'Reilly. And he gave this brilliant talk, Programming with Nothing. And to follow up on a discussion I had yesterday, yes, he does actually create church numerals and then do it from that, because in Ruby it's much less of an issue running out of stack. So, oops, let's go back, because the other, not touchscreen, isn't touchscreen, don't try and touch the screen. Thank you. This chap, Jim Myrick, unfortunately is no longer with us, but he did a brilliant talk just on the Y Combinator at RubyConf in 2012. The reason that I actually started taking functional programming seriously because Frances Campoy Flores decided to give a trolling talk about how you couldn't do it in Go. He's wrong. And last year I gave a simpler but more detailed on the functional programming side version of this talk. Don't touch the screen. No, don't. It's not touchscreen. Thank you. I have a book. It doesn't have this stuff in yet, but it does have some other weird stuff. You can get it on Leanpub. I will finish writing it when I die. There's only one edition. You pay once. They do sales. It goes for $8 a time when it's on sale. Buy it on sale. I don't care. I've got a GitHub. It's full of code you should never use in Go. I've got a SlideShare. It's full of things you should never do in Go. Thank you very much. You've been a brilliant audience.
Thank you very much, Ali.